Well, welcome to week 5. We are going to be talking about chemical etching and introducing you to the concepts um, of macro and micro etching. Looking at an overview, we're going to discuss the purpose of etching, and before we move into macro and then microscopic, the microscopic techniques will involve electrolytic etches, chemical etching, and the use of colored etchants. So what's the purpose of etching? Metallographic etching is essentially used to reveal the structural characteristics of the material through controlled preferential attack on the metal surface. The two categories of etching would be macroscopic, that you can observe with the without the use of visual aid like a microscope, um, and then you have microscopic etching, which is a technique that will be utilized where you would then observe the structures under a microscope and or scanning electron microscope. The standards that are typically associated with macro etching is ASTM E340, and for micro etching of metal alloys would be ASTM E407. So macro etching. This helps reveal any homogeneity within the materials on a macroscopic level. Such features will include grain size in terms of flow lines, dendrites, columnar structure, etc. Um, Segregation, dealing with chemical inhomogeneity, banding, coring. You can even utilize it for determining carburization or decarburization depths within materials. Discontinuities of, let's say, for instance, weld seams. If you wanted to find a weld seam, and within that weld seam you have porosity. How about cracks? Determining where those cracks are emanating, ID, OD, are they in the heat affected zone, so forth. And then, of course, in the fabrication and manufacturing process, um, macro etching is typically used in a lot of the welds. So once again, weld structure, determination of weld penetration, um, to find locations of hard spots, which could also be detrimental to a material, etc. So once again, these are the different kinds of features that you can see without the aid of a microscope. So where are these applied? The steel industry determines the tone of these billets with respect to inclusions, segregation, and structure in which they use for quality control. Forging shops determine flow lines for best forging practices, design for the die, and also metal flow. Copper industry, not everything is derived around the steel industry, but the copper industry does it for control of porosity in wire bar, and the aluminum industry uses it to evaluate their extrusion process or other forging products for defects such as coring and or cracking. So what's the difference between macro and micro? So we already went through the metallographic preparation process where we did a coarse grind, coarse polish, fine polish to a mirror finish. It turns out that with macro, once you select your sample, for instance, let's take a steel billet. They'll take the sample. So they'll make a billet would be, just think of a long rectangular or square shaped piece of hot metal, and then of course when it cools they'll take two transverse cuts and they'll macro etch that surface. Typically that disc will be taken at near the end of the billet. Sample preparation. obviously these billets, they're huge. They're not going to be something small. And if you're trying to look for segregation, cracking, um, anything along those lines, you're looking at, you know, 10 square inch. You could even look at samples that are 5 by 5, 25 square inches um, in area. And the polishing tables are only 8 inches in diameter. So it would be difficult to uh, manipulate and then polish that sample on standard metallographic tables. So what they do is you're able to turn these on a lathe. So you're able to mill off the top surface with a kind of like a rough cut, and then follow through with a fine finished cut. And then you just clean the sample of any debris, lubricants, or oils. Because when you go to etch, you don't want you want to prevent any uneven etching, uneven attack when you etch. And then when you etch, these are typically performed using immersion or swab techniques until the structure reveals itself. Once the structure has been revealed and you're satisfied, then you'll rinse it off with hot water, and then you can dry it under a hot gun, or just blow it off with compressed air. So an example of what one might look like, this is a 5-inch by 5-inch billet. So the image that you see on the left is a disc that's been cut transverse, and this is of a continuously cast type 430 stainless steel. And what the macro etch has provided us is the ability to look at the grain structure throughout the entirety of this sample. So you're going to see that it's got 3 zones in this structure. The first zone is right on this surface, and this is a fine equiaxed grain structure. Fine, that means the grains are super small, and it's right at the surface. Your second zone are columnar grains. So you can see that the grains look like they're growing or elongated inward towards the center. And that goes to the third zone, which are large or coarse equiaxed grains at the center of the billet. How do these 3 zones come about? Well, when you're looking at this continuously cast product, the reason why you have smaller grains on the outer surface is because those experience the quicker cooling rates. As a continuous cast billet moves through, it is sprayed with water to cool that outer edge. So this is the first to solidify, is your surface, giving you the smallest grains. Now the rest of the material is going to cool slowly, but because you now have a gradient where it's cooling here and it's still very hot in the center, your grains will grow in a columnar structure. And until it gets to the very center where the billet is still hot, the grains are going to be larger because they cool at a much slower rate. So this is one of the reasons why the steel industry likes to use macro etching in a quality control environment, is because they want to make sure that they're getting the product that they want. Now, something else that comes out in this particular billet, the 2 red arrows I have do indicate that there are cracks in this billet. Cracks are bad, yes, if this was the final and finished product. Now, one of the things is this is a ferritic stainless steel. Chances are this is going to go through a different type of process after the billet has been formed. Typically, it'll go through a hot rolling process. So once again, under higher temperatures, it gets hot formed. So those cracks will actually mend themselves and seal, and you will not have an issue unless those cracks were filled with oxides and or slag from the casting process. So that's an example of a macro etch. You can see, like I mentioned, this is a 5-inch by 5-inch billet. So large piece. If we go microscopic, then I have 3 different techniques that I could utilize for the microscope. And this is where you're really going to be interested in what phases are present. Going back to the macro, you're not really interested on what phases are here versus here or here. At this moment, you just want to see what the grain structure looks like, what the flow lines are indicating. Are there cracks? Those are the some of the reasons why you would do a macro etch. For microscopy, you would typically use it because you're now interested in, well, how much retained austenite might I have in my steel sample? How much martensite versus bainite do I have? Do I have carbides? That's where the technique of microscopic etching comes in play. So once again, you have 2 different types of chemical etching techniques. The first one is immersion. This requires your polished sample, so mirror finish, to be face up with the etchant, with enough etchant to cover that surface. Typically, when you do an immersion, you'll have to find a way to agitate the etchant in order to produce a fresh etchant on the surface. You're probably thinking, well, it's immersed, so wouldn't it be fresh all the time? But if it stays stagnant, there's no flow to really bring on fresh etchant to that surface. So the fresher the etchant, the faster and more uniform the etchant will attack that surface. Swabbing is by far the most commonly used technique. One of the reasons why is because it uses far less etchant and far less waste is generated using this process. What this technique typically does is it requires the user to load the etchant on a cotton ball or cotton swab. I prefer cotton balls over cotton swabs, and I'll explain that later. And then you gently apply that to the sample, dabbing. And this is, of course, my favorite part because I would have dabbed in class. But you'll dab the sample to kind of mimic the fact that you're applying fresh etchant to that surface, so you get a uniform attack across. In both cases, once the samples are, satisfactory, you'll rinse them, hot water, warm water. You'll have to dry them before you evaluate. So when you rinse the sample, not only will you rinse it with water, but then you'll want to rinse it with enough ethanol, or you can even ultrasonicate it to make sure that you do not have water on the sample. So when you dry it, you stain the sample less, making your evaluation less painful in case you don't like stains on your sample. The electrolytic etching technique is you're essentially applying an electrical potential to the specimen using an external circuit. So you'll apply a voltage, and what happens is the positive metal ions will leave the surface and diffuse into the electrolyte that you have in contact with your specimen. So what are some of the advantages of electrolytic etching? Is the fact that you can also use an electrolytic polish and etch are both possible. They're both very fast, and it's reproducible. And the reason why they're reproducible is once you find the correct voltage and time of exposure and use the correct electrolyte, you can reproduce the same etch on every sample that is very similar to the one that you are working on. So, for example, if I wanted to electrolytically etch a 4140 steel, it would have a specific electrolyte, a specific voltage, and a specific time at exposure. And of course, the temperature of that electrolyte is going to matter. So the moment I optimize that, every 4140 sample I come across from now on will have the exact same etch technique. Now that's pretty neat because especially if you're going to do any type of comparative analysis between, let's say, vendor A versus vendor B that both have a 4140 sample, and your client is trying to identify, well, they're claimed to both have the same mechanical properties. I just want to make sure that they're both the same chemically and microstructurally. So that would be one nice way of doing it. Obviously, if one person has a 4140 and now you want to electrolytically etch an Inconel 738, which is a nickel-based superalloy, you have to find now a new type of electrolyte, identify a new voltage, a new time, and of course temperature is always going to be a factor. So some of the disadvantages of the electrolytic etching technique is the fact that, well, for one, you're applying an electric potential, so that means your specimen must be conductive. One of the things that can happen is if the etching voltage is too high or the time at voltage is too long, you can cause preferential attack or pitting can occur in your sample. And once again, if you're trying to identify true microstructures and you see pitting in your sample, the first thing you're probably going to say is, I have porosity in my sample. So that also leads to why we look at our samples prior to any etching technique that we will perform. Unlike the chemical etching process, if you have a 2-inch sample, at least with a cotton ball, you're able to cover the entirety of that sample to identify the microstructure from end to end, surface to surface, versus the limited etching area that you have with the electrolytic technique. Typically, these are small windows, and you'll only partially etch your sample. So now it's going to be a determinant on where you placed your sample on that window. Your electrolytes are pretty hazardous. That's always an issue, right? Now you're dealing with more hazardous chemicals. Temperature controls are vital. So if you're using a hot electrolyte, it will etch your sample differently than if it was at room temperature. So in order to identify time, voltage, and the electrolyte used, it does require more experience than the chemical etching that you would do with a cotton swab or immersion. So here's an example. I have a sample of Inconel 738, nickel-based nickel-based superalloy, and this is in the as polished condition. So after 1 micron diamond suspension, this is what my sample looks like. The image on the left is at 100 times magnification, and the image on the right is at 1,000 times magnification. Okay, and so just to emphasize the importance of why I'm looking at this in the as polished condition, are the fact that turbine blades, majority of them are all cast products, and typical cast features are dendritic structures and porosity. So I want to make sure I capture those features in the as polished condition prior to any etching technique that I decide to go with. So this image here on the left, this right over here that I'm circling with my little fingers, that's porosity. Okay. These other darker specks, if to the untrained eye, you're probably going to say, oh, that must be more porosity, or, you have gunk on the surface. It's as polished. How can you reveal any microstructure? Well, to be honest, all of those little specks that you see are carbides. And so at a higher magnification, I have a little tiny thing of shrinkage porosity here. And these gray features that you see are carbides, and those are dispersed throughout the alloy. So now I'm going to etch this sample, and the first attempt is to look at the general microstructure. I don't want to etch the sample with a special etchant without looking at what the general microstructure looks like. So I etched the sample with Calling's #2 reagent. It's a very typical etchant for a nickel-based superalloy. And you can see that these grains, you have grain boundaries that are now easily defined. So this image here, once again, is at 100x magnification. And in that image, I have 3 grains present at 100x. Okay, that is showing me that I have a very large grain structure. Okay, and I should for high temperature materials. I'll explain that stuff later when we get to superalloys. But for the case of what we're looking at here, you'll see features that are, for one, each of the grains are a different shade of gray, 50 shades of gray, different shades of gray. The reason for those different shades are two different things. The first is the crystallographic orientation of that grain. And how it reflects light back is determined on the brightness of that grain. The features that you see within the grains are what we call dendritic structures. So you have coring occurring. So you see this brighter feature in the center, and then it kind of darkens around here. Well, that is just the dispersion. That's the inhomogeneous or chemical segregation within that grain as it's solidified, giving you this type of coloration and texture. Okay, so the last portions to solidify are going to be where our carbides are sitting, and they're sitting in the interdendritic spacing of our dendrites. I still have porosity, and the porosity is located at grain boundaries. This right here is at a grain boundary. Makes sense because as it's solidifying, when a metal solidifies, it shrinks. So it will shrink in areas where the grains would come together. So at a higher magnification, which is 1000x on the right, you're going to see now I have the grain boundary, and I'm looking at a bunch of these little specks within the grain. Okay, I have our darker, I should say gray carbides within the grain. I have grain boundary carbides that are located at the grain boundaries, but I'm still not sure what all these little guys are that are in here. So when we are assessing turbine blades, we have to not only look at the features that we see in the general microstructure to identify if we have acicular phases, which are, you know, embrittlement conditions, signs of overaging for a turbine blade, but we also want to make sure that we have and are able to identify our precipitation strengthening method, which in the case of a nickel-based superalloy, it would be gamma prime. So I have to then go back and repolish my sample. I don't have to start all over again. I just have to jump back to maybe a 3 micron or 1 micron on the flat nylon pad or low nap cloth, and I then perform an electrolytic etch. This is the same turbine sample, okay? Very different. I am at 100x on the left and 1000x on the right. Now you can see the gamma prime. The gamma prime in this case looks evenly dispersed. You do not see an agglomeration of it. I do have carbides sitting in the grain boundaries. Okay, I do have carbides within the grains. I still have my shrinkage porosity located at the grain boundaries. So this is the technique that I would then perform gamma prime measurements in the SEM. And that would determine whether or not I have seen any thermal degradation of the microstructure to deem these no longer serviceable. Colored etchants. A colored etchant essentially is, we call it an interference film, and that film can be produced by either heat tinting or through a chemical process, and this is all known as tint etching. So what you're really doing is you are processing, or I'm sorry, not processing. The process of it is essentially the deposition of a very thin film, whether that film is an oxide film, sulfide, chromate, phosphate, or molybdate film. It's going to cause coloration by interfering with the light from the light microscope. Okay. And the coloration is also dependent on the crystallographic orientation, and can also be influenced by chemical segregation, residual deformation, and also the thickness of that film will have an influence on color. So this is a very tedious and sensitive type etching method, but it does have its uses. Not to say that colored etchants need to be used for everything that you are working on. Generally, just your straightforward chemical etchant is best. But when you use color, let's look at the difference between this copper zinc alloy. So this is 90% copper, 10% zinc. The image on your left, this is the same alloy, okay? The image on your left was etched with a potassium dichromate, which is used for general microstructural characteristics, just to reveal the general microstructure. And looking at that microstructure, what I'm looking at are, I see a decent sized grain here, and all of a sudden, oh man, that's a large grain, and wow, this must be a large grain here. The real microstructure hasn't been revealed. And one of the things that you do not want to do is over etch your sample, because what you're essentially doing is eating away the material. And when you eat enough, if you eat away the material enough, you're going to create an unevenness when it comes to focusing, especially at higher magnification. So both of these are shot at 100x magnification. And the reason why the grains over here look like there are smaller and I guess say a larger quantity is because if you were to look, and I can zoom in because I remember I have my magnifying glass. So if I were to zoom in really close, what I thought that was a large grain right here is actually one, two, this one right here. I mean, you might have 1, 2, 3, 4 grains, but it looks like one. Okay. Sometimes the etchants, it's going to depend on crystallographic orientation and the energy at the grain boundaries on whether or not you get a delineation there. Okay. So with a colored etchant, since it is highly dependent on crystallographic orientation, you go to that same sample and you look over here and look how small some of these grains are. Okay, so it's able to pick up those grains. You can easily come in here and say, oh, that's a grain. Oh, and then this one right here is a grain. And there's another grain, and that's a small grain. You don't have to play the guessing game like you would over here, thinking, oh, this is one large grain right here. Okay, so the colored etchant in this case brought about the true microstructure for this material. So looking at your assignments for the week, once again, this Friday, hopefully everybody's got their EH&S safety certificates, or at least are signed up to get it completed this Friday in order to not receive a penalty. The complete your weekly summary, once again, Sunday end of day. A quiz will be posted also Sunday at the end of the day. And I would say start preparing for the first exam, which will be held in our classroom in the computer science building on February 26th. We can start the exam at 1 and end at 2, which would give us enough time in the lab then to stagger through and cover etching and microscopy. So I will be handling the etching aspect of it, and then Wayne will be helping with the microscopy, just to show, you know, how to use it, how to take pictures, and things like that. This exam will be in person. The 3 that are not able to make it, I will be making special arrangements for the exam for you guys. But everybody else, it's going to be in person for that Friday. Okay. I will be signed on Friday during our lab this week, even though we do not have lab physically. It turns out one of the other instructors has had a snow day on Monday, and they're going to take that Friday, which actually works better for us because after I etch a sample, I have something to show you then for microscopy. So it works better for us that way. So I look forward to seeing everybody on Friday, hopefully. If you have any questions or concerns, we can address anything and everything during our lab time on Friday this week. And I will be preparing the examination for next Friday. I have not written it up yet, so I would not be able to tell you what's on it as of right now. I have a feeling I won't write it until the weekend anyway. But remember, since this is a 1-hour lecture portion of the course, the test will not be longer than 1 hour. Hence the reason why I said from 1 to 2. Okay. Till then, I hope some of these etching techniques will come in handy. Remember, in your weekly summaries, if you learn something new, a new technique, or a new bit of information, new concept, new terminology, please state it. But how could these techniques help your research and or lab experience or industrial experience as well? Um, I'm enjoying reading what I've done so far for your weekly summaries, and I look forward to hearing more feedback from you guys when you submit them. Have a good day, and I'll see everybody on Friday.